can we start?
Yes, Ankush, I think we can start.
Okay, thank you, sir. So, a very warm good morning to one and all present here, and I welcome Professor Arun Nayak to the short term course. Today, he'll be delivering his second talk, and it's day 4 of the short term course. Today, Professor will be discussing about Monte Carlo methods, and now I'll request Professor Arun to start the talk.
Okay, thank you. Okay, so this is the second talk, as I said. So today I'll be discussing some basic things about Monte Carlo simulations. Okay, let's see what is called the Monte Carlo techniques. So Monte Carlo technique is basically a numerical technique, to calculate some probabilities and related quantities like mean, sigma, and all other quantities which are related to probabilities. So using a sequence of random numbers. Okay. So the typical procedure for Monte Carlo technique is that you generate a sequence of random values, say R1 to Rn, according to some uniform distribution which can be distributed between 0 and 1, and then you from this distribution you determine another set sequence, say x1 up to xn, which are distributed according to some PDF or some desired PDF, so PDF that you want to have, for your problem. And then these values of x, you can treat them as simulated measurements, so equivalent to what you are expecting, what you expect from a given experiment, for example. And then you can use them to compute the probabilities for x to be in a certain region. Say like probability for x being between a and b is integration of a to b f of x dx. That means basically you compute the area under this curve f of x between a to b. Okay, so that is the standard procedure for doing any Monte Carlo techniques. So what we are saying is that Monte Carlo calculation is nothing but doing some kind of an integration over this PDF. Okay, the random numbers are distributed according to this PDF. So this technique is most useful when other methods, like any other method for doing Monte Carlo for doing numerical integrations, are not feasible. Like there are many other numerical integrations, like integration methods, which are also used for doing integrations. But if those things are not feasible, then you can use Monte Carlo techniques to do such kind of for such kind of problems. For example, if you want to do an integration over a joint PDF f of x, where x is many variables, not just one, it's vector of variables, over a complicated region. So you do not know, the functional form is not very simple, so you cannot apply other integration methods. In such cases, this will be more useful. Okay, so what are the basic ingredients? So for performing Monte Carlo simulation, we need at least 4 crucial ingredients to understand the basic concept of Monte Carlo strategy: random variables, then probability distribution functions, moments of the PDF, and their pertinent variance, sigma square. I think all of this have been already discussed in your probability lectures, so I will not go through them that much. Just say give an example. So let's consider a tossing of 2 dice together. Okay, so each dice has numbers 1 to 6. So if you are tossing 2 dice together, what are the outcomes and their corresponding probabilities of getting a particular number on the 2 dice? Say if you are tossing two dice together, what is the probability that we get 6, sum of the two numbers becoming 6, for example. So when you toss these numbers, you will yield, following possible outcomes from 2 to 12, right? So if you add the two, so these values are called the domain, the numbers that you are expecting from these experiments, and the corresponding probabilities to get each of these numbers are given here. So 2 you can get only once, because if both of them are 1 and 1, so the probability to get 2 is 1 over 36. Okay, but 3 you can get 2 possible ways, so it is 2 1 or 1 2, so you have 2 over 36 and so on. Okay, so these numbers have different probabilities to obtain them when you are throwing the two dice together. So but when you are tossing, you cannot tell beforehand that what will be your outcome, whether the outcome will be 3 or 5 or 7, you don't know. Okay, so that is the randomness. So you do not know beforehand what you are going to get, but what you know is that what is the probability to get such number. Okay, that certain number will appear with a certain probability. So random variables are characterized by a domain which contains all possible values that the random value may take, and this domain has a corresponding PDF. So this defines your PDF. Okay, this probability distribution. Okay, so I think, yeah, I can give another example. So this is from physics. So consider, say, a radioactive decay of an alpha particle from a certain nucleus. Okay. So if we have a detector, in this case, we can detect them using, say, Geiger-Müller counter. So that registers, for example, every 10 millisecond one alpha particle, whether an alpha particle reaches the counter or not. So if one observation means one hit and no observation means 0. So if we repeat this experiment for a long enough time, the outcomes of the experiment will be truly random. So we cannot say whether will get something or not at a particular observation beforehand. So, but if we repeat it for long enough time, we'll get a probability distribution. So that probability distribution will have this exponential form. Okay. So this is the distribution we'll get, where mu is your half-life of the nucleus that decays. Okay. And x in this case is actually the time. Okay, so then I will not go through this PDF and CDF. I guess you already had enough of this in your previous lectures. So I hope that you know that what is PDF and what is cumulative distribution functions. Then PDF of a function of a random variable and how to get them. Now let's come to how to generate random numbers. So the goal is to generate a sequence of numbers which are distributed randomly according to a uniform probability distribution. Starting from a uniform probability distribution, we can go to a desired PDF. Okay. So first goal is to get an uniform probability, a random numbers distributed according to uniform probability distribution. So what should be its property? First of all, it should have long periodicity, because otherwise you will keep repeating the same numbers. Okay, so then they will not be truly random if you have repetitions of the same number. So if you are using some kind of, say, 32-bit integer, the period typically appears to be something like 31 minus 1. So this number gives the periodicity. After this many numbers, you will get a repetition of the numbers if you are using a 32-bit integer. Then another thing is that they should have best randomness, like the correlation among the generated numbers should be small. That is the correlation between, say, xi and xi plus l. No, the distance between l is the distance between two numbers. Okay, they should be uniform for l not equal to 0. Okay, that means they should have no correlations between say ith number and I plus L number or I plus some k numbers and so on. So they are not correlated. So these two properties should be satisfied, or at least uh, some level, so that we can use them to we can treat the numbers to be a random number. So there are two types of generators. So they are called two random number generator, which are based on physical phenomenon like say radioactive decay. So you just have a radioactive nucleus, and when it decays, you count it, okay, as one random number, or say atmospheric noise and so on. So they are truly random. Okay? So you cannot know what is going to come in the next. Then there are pseudo-random number generators, which are basically computational algorithms which can produce long sequence of apparently random results. Okay? But mostly we'll concentrate on pseudo-random number generator, because pseudo-random number generators also allow you to reproduce your results. Okay, suppose you have calculated something with random number, you want to recalculate this the same thing and check that you did something correctly or not. You can generate the same sequence of numbers, and also you can have large number of such random numbers when you need large statistics, large sample statistics. Okay. Okay, so as I said, pseudo random random numbers are not truly random. So they always produce same sequence of numbers if the input is same. Input means you start with some number which we call as seed, and if the seed is same, then the sequence of such numbers would be basically same every time you generate them. And the series of numbers generated by these computational algorithms is generally determined by a fixed number, which, as I said, seed. And you can use such sequence of numbers as random number if it satisfies some properties of the random numbers, okay, like these correlations and so on. So advantage is that it is uh, you can have high speed, so you want to produce large number of such numbers very quickly, and also reproducibility, that you can reproduce the same sequence of random numbers every time, so that you can test your calculations second time as well. So that's why these pseudo random number generators are central in applications such as Monte Carlo simulations. So all the Monte Carlo simulations that you normal people do using computer, so you just pseudo random number generators. So the most common is this multiplicative linear congruential generator, which are typically looks like this. So given a number xi, you generate a next number xi plus 1 by this algorithm. Okay, so you use axi plus b mod c to get the next number, where a, b, c are some large integers which determine the quality of your generator. Okay. So here is an example for you to write and see that they are truly random. So write a program to generate uniform random numbers. It should be just 3-4 line code. You choose random number between 0 and 1. You choose a as 7 to the power 5. You can choose b to be 0, and c as 31 minus 1. So c determines the periodicity of your number. Okay, so if c is a 32-bit integer, okay, then your periodicity is given by this. Okay, in some cases you may want to have different sequence of random numbers. Say for example, you are trying to produce large set of samples, but you cannot run your computer for 1 month continuously. Sometimes power failure happens, your computer might be dead and so on. So you would like to have large set of events or some simulation, but you want to produce it, in different sets, okay, but you don't want to repeat them. So what you would like to do is you change your seed every time you start the sequence. So you can do that manually. You can change your seed manually, okay, so that uh, you get different sequence, or you can change your seed automatically by, for example, using the time at the current time as your seed. For example, here one uses the current time to get the seed. In that case, you write your sheet taking into account the current time. Time, these numbers are the defines your time of the moment, and then every time you run the sequence, you get a different set of random numbers. Okay? So that is also possible, and most of the high-level programming languages already have these options to do this. So you can just use any of the programming language to generate a sequence of random numbers between 0 and 1. Okay. Then there are actually many types of these random number generators with a different periodicity. I just give one which is quite uh, frequently used. It's called Mersenne twister generator. So this has a period length to be something like 2 to the power this large number. Okay, so it is really very large, and this its period is chosen to be a Mersenne prime. So it's been by this, and it is implemented in a way that it is quite faster. I mean, in our case, we have this. If anyone is related from particle physics using the so-called this root framework for data analysis, it already has this one. But okay, maybe there are other packages which can also may have also already this generator. Okay, you can go through these references if you need more information about this. Okay, now I come to use of Monte Carlo method. So given that we have sequence of random numbers, how we use them to do our Monte Carlo simulation. Now let's consider the evaluation of an integral using some numerical methods. Okay, so we know many numerical methods like trapezoidal rule, midpoint method, I think Simpson's rules and so on, right? So you have many uh, Newton Cotes quadrature methods we know, also Gaussian quadrature methods, which are used to perform numerical integrations. Now let's take one such example. Suppose we want to do this integration of this PDF f of x dx between 0 and 1. Okay. So typically in Newton Cotes method what we do is it is equal to this sum, okay, goes from I to n are the number of points, grid points, which then we write wi f of I. Wi are the weights at each grid points, right? So, for example, this Wi are evaluated using Simpson's method. Okay. Now, let's take the very simple one, the midpoint method or the rectangle method. Okay. So, in that case, what you do is the weights are all 1 and the f of x are evaluated at each midpoint. Okay. So, the integral is approximately h is the step length or distance between two grid points times sum of f of xi half xi minus half are the midpoints between the two points, right? That's what we do. Now, and h is your b minus a by n, or in this case the b minus a is 1, so it is 1 over n. So what we write is I equal to 1 over n of this sum, right? So this is what we do in the midpoint method. Now, suppose we are calculating the average of this function, okay, function f of x for a given PDF P of x. So if we know the PDF P of x, then we can calculate the average of this function f of x. Okay. So the definition of this average is that 1 over n sum over I.
Uh, Arun sir, kindly unmute your mic. I don't know how it has been muted.
Okay, thank you. I think there are some noise. I think probably somebody muted everyone. Okay, thank you. So yeah, so if we calculate the definition of the average that it is 1 over n times sum of pxi times f of xi, where pxi is the PDF and f of xi is your function, right? And we generate large number of such xi's. So now suppose we consider a uniform PDF. So p of x is 1 between 0 and 1 when x is between 0 and 1. In that case, then the integration of I is same as your average. Okay. So if we calculate simply, if we generate a random number between 0 and 1 uniformly and then calculate the average of this function for this set of random numbers, that will be equal to or almost equal to its integral value. Okay. So as you can see, integral is nothing but this average over this your samples. So such approach of doing the integration, generating the random numbers between 0 and 1 uniformly, is called this crude integral method or crude Monte Carlo method or brute force Monte Carlo method. Okay. So let's see what is the accuracy of such methods. Let's calculate the variance, the sigma square of your function. So sigma square we can write like this, right? Which is 1 over n times sum over f of xi minus mean of x, f square times pxi, pxi is your PDF. That is how we calculate sigma. Then if we take p is uniform, then this becomes sigma f square becomes like this. Okay, so which is nothing but f square average minus f average square. Okay, so which means it is the measure of the extent to which f deviates from its average value over the region of your integration. Okay. Now consider that the previous result that we obtained is some fixed value of n. So n number of measurements. Okay. N number of points or n number of random numbers. So that we consider as one measurement. Okay. Now we repeat the same calculation for m such different measurements. Each time we generate n such numbers. Okay. Then we can write the integral as the average of m such averages. We can improve the value by doing such averaging. So then this average will become average of such averages. And then if we consider the probability of correlated events to be 0, that every time we are actually generating new sequence of numbers, not there are no repetitions, okay, there are no correlations between different sequences, then the variance of this series of measurements can also be written like 1 over f times the variance of individual measurements. So that means the variance will decrease by factor n, okay, or the standard deviation will decrease by factor of 1 over square root of n. So if we have large number of measurements, then we will decrease by factor of n. So now this is we consider n measurements, m measurements. Now we can treat each number as also one number.
I would like to request all the participants Kindly keep yourself muted. I don't know who is she.
Okay. So then we can consider each random number, one number, as one measurement. In that case, the sigma itself, which is also proportional to 1 over square root of n. Okay. So now let's compare this to any other numerical integration based on this Taylor series expansion, like a Newton-Cotes method, right? So, for example, trapezoidal rule. In trapezoidal rule, the error goes like order of h to the power k. Okay. For any Newton-Cotes method, the order goes like h to the power k, where k is equal to 2 for the trapezoidal rule. Okay, h is your step length. Okay. So that means if you have n points, okay, between B, A and B, so the error would go like n to the power minus k. Now consider some integration in very high dimension, not one dimension, say like large dimensions d. Okay, so we are performing an integration in a volume of a hypercube, okay, with side L and dimension d. Then the number of points in that cube n, if we generate n number of points in that cube, so this will be L by H times d. Okay, so the error in this case will go like n to the power minus k by d. Okay, so this numerical integration, if you are choosing n points, then in this case the error goes like n to the power minus k by d. Now, if we perform the same integration using Monte Carlo method, the error will still go like 1 over square root of n. Okay, it doesn't depend on your dimension. So when d is larger than say twice k, okay, in that case, so in this case, if d is, or if we use say trapezoidal rule, the d, if you do trapezoidal rule for dimension 4 variables, for example, okay, in that case it will be worse than the Monte Carlo method. The Monte Carlo method will perform better than this, but of course for one dimension and for simpler functional form, these numerical integrations would be better. So the numerical integrations, as the Monte Carlo methods, have better accuracy than the traditional numerical methods for higher dimension and for complicated regions when the standard numerical method is not easy. Okay. So I give some exercises. So if you have time, you can do this. Then you will understand better. So just generate some random numbers using uniform random number for 10 plus 6 sampling points, and then calculate the integral for x square dx between 0 and 1, and you know what is the value of x square dx, and see how much is the accuracy for these numbers. Similarly, you can perform also an integration this one, okay, and you compare this to the exact result. And you can actually check as you increase n, what is the improvement in your accuracy. Okay, I tell you another example. Suppose you have a box, okay, so you have a box with a wall in between, okay, with a small pore. Now you have, in the beginning, you have n particles in the box, okay. Now you want to find, as time passes, what is the number of particles. As time passes, there will be one particles will move from one side to the other side, right, through this pore. Now as the time passes, what is the number of particles on a given side? That is what we want to know. You can actually solve such this one analytically, which I will tell you. Okay. Now you know what is the analytical result. You can try to do the Monte Carlo simulation to see if your analytical result matches with your Monte Carlo simulation matches with your analytical result. Okay. So at time t equal to 0, you have this portion as n particles. At each time stamp, you have probability for one particle from going to left to right or right to left. But going right, this depends on the density of these particles. Okay. So suppose at a given time t, you have nl particles in the left and nr particles in the right. So sum of nl plus nr is total n. Okay. So for each time step delta t, you have the probability to move the number of particles to the right is nl by n. The number of particles in the left divided by the total number of particles. Okay. Now, to simulate such system, so what we can do a simple algorithm. So we loop over these time steps, choose t max as greater than n. Okay. T max, the total time is much greater than n. Then for each time stamp, generate a uniform random number between 0 and 1. Okay. Now compare this number to the probability for the particle to go to right. The probability for the particle to go to right is nl by n, right? The number of particles in the left divided by the total number of particles. So if x is less than this, then you move one particle from left to right, or if x is greater than this probability, then you move one particle from right to left, because the probability for the right side to go to left will be more. So if you do this for large enough timestamps, then you will get this kind of results. So you will see this curve as a function of timestamps. If you plot nl, the number of particles in the left, so it will slowly will become small, and then at a particular after a certain time it will be in equilibrium. That means it will have approximately same number of particles in both left and right, and when they are same, they have almost equal probability for left going to right or right going to left, then they will be in equilibrium. So you can see that, and you can derive this actually with the analytic solution, and you will get nl t equal to n by 2 1 plus e to the minus 2t by n. So I I ask you to derive this, and this function, the analytical one, is also shown here as a dotted line, and you can see that this curve, solid curve and the dotted curve, are almost on top of each other. Okay, so this is one of the exercise. There's another exercise you can do. Okay, this is for physics students. If any of you are from physics, suppose you have two nucleus. You have one nuclei, bismuth, which decays through a beta decay to polonium. Then that one also further decays through emission of an alpha particle, okay, to lead, okay, which is then stable, so it further doesn't decay. So it is a two-body decay. So starting with say bismuth, you reach lead. Now suppose this one, bismuth, has a lifetime of 7.2 days, while polonium has a mean lifetime of 200 days. Okay. Suppose we start at time 0, then and we have initially tender 4 bismuth nuclei and 0 polonium nuclei. Then at a given time, see what is the number of bismuth, bismuth nuclei, and what is the number of polonium nuclei, and what is the number of lead nuclei. Okay. So that you can do through simulation. In fact, you can also calculate analytical solution for this. So you will have this coupled equation for two nucleus, okay, and then if you solve it, you will get this kind of analytical solution for finding the number of poloniums at a given time t. And you can do this similar kind of simulation to see how many or whether it matches to your analytical solution. You can do it. If you cannot, you can ask me. I have a small piece of Python program I can give you to check. Okay. So now let's come to central limit theorem. I guess you already have studied it in your previous lectures. So I just state this. What is it? Suppose we generate a series of random numbers, random variables xi from a PDF p of x. Okay, so we have many xi's, and we know the mean and standard deviation of px, which are mu and sigma. Then, if we take an average of m such random variables xi, x1 to xn, and this average value is z, then what is the PDF of z? So it states, this theorem states that in the limit m tends to infinity, that means m is very large, the PDF of this average will be a normal distribution, a Gaussian distribution. Okay? The PDF of z will be Gaussian distribution with the same mean, and the sigma will be sigma over square root of m. Okay? So this also I told you yesterday, okay, when we discussed the intervals for the Gaussian parameter. I said that the PDF of sum of many random variables becomes Gaussian, so this is relevant in many cases. Okay. Now I give you an example again to check this theorem using random numbers. So first, before going to large number of random numbers, adding large number of random variables, you can add simply two random variables x and y. Suppose x is 1, x and y both are uniformly distributed between 0 and 1, and you add the two. So what will be the PDF of z? So you can calculate this. So how do we calculate the PDF of z? The PDF of z will be PDF of g of x times h of y, right? So we have times dx, or we can say like g of x h of y dy, okay, where g and h are the PDF of x and y. Okay. Now if x and y are uniformly distributed between 0 and 1, then g of x is 1, h of y is 1. So we can write f of z is between 0 to 1, h of z minus x is dx. For z minus x is, we have to see what is the value of h for a given z minus x. Okay? Because z will go from 0 to 2. If x and y goes from 0 to 1, z goes from 0 to 2. Based on as z goes from 0 to 2, we have to see what is the value of h. Okay. Now we can find what is the value of h. So h has to be 1 in some region of z and 0 in some region of z, because h is a PDF for y, right? So when z minus x is between 0 and 1, h will be 1. When z minus x is between 1 and 2, h will be 0, right? So let's consider when this will be 1. So let's consider for two regions of this integration between 0 and 1 and 1 and 2. Okay. So when z is between 0 and 1, y will be between 0 and 1 only if z minus x is greater than 0. Okay. Then that means x is less than equal to z. So this condition will be satisfied, and then you can put that condition here. So then this integration will be replaced by 0 to z, because from z to 1 y becomes h becomes 0, and that gives you z. Similarly, you can do the integration for the second case when z is between 1 and 2, and you will get this integration to be 2 minus z. So what you get, that between 0 and 1 the f of z is z, between 1 and 2 f of z is 2 minus z. So that is nothing but a triangular distribution. Okay. So you will find a triangular distribution for z. Now this is for two numbers, we just added two numbers. Now when we add large number of such numbers, practically about 20 or more, you will see this triangular distribution slowly tends to a Gaussian distribution. Okay. So for large enough numbers, it will become a Gaussian distribution. So these are the exercises you can try to do. So generate, say, two independent uniform numbers x and y distributed between 0 and 1, and then plot the distribution of z. So you should see that it matches the one that we derived in the last slide. It should be a triangular distribution. And you can do the same exercise for large number of similar random numbers, okay, which are all distributed between 0 and 1, and you should get a Gaussian distribution, and you should verify the result against the central limit theorem. You can repeat this exercise too for a mixture of different type of PDFs. Like you generate not uniform, but you can generate exponential distributions and Poisson distributions and so on, and then add them together to see if they become Gaussian. Thus, the average becomes Gaussian or not. If possible, you can do the last exercise as well. You repeat the same exercise for Bright-Wigner and Landau, okay, and see if they still obey central limit theorem. If not, find out the origin, because I guess it must have been taught in your PDF lectures. Okay. Now let's see. Till now, what we discussed is that we discussed about uniform random numbers, or random numbers with uniform PDF. Now, how do we go from uniform PDF to a PDF of a desired size? Okay, a desired set. So suppose we want to have a PDF not uniform, but not between 0 and 1. We want to go from A and B, or we want to have a Gaussian PDF or an exponential PDF, right? So how do we generate such numbers? So if we want to go from one distribution to another distribution, okay, then we can use a conservation of probabilities. Suppose Px is generated, x is generated with uniform distribution, so Px is uniform, and we want to get a PDF for y with a we get a different random number y with a different PDF f of y. So we can use this conservation of probability, and then Px is 1, so dx becomes f of y dy, and so x x, which is a function of y, will become integration minus infinity to y f of y prime dy, right? Then y is basically inverse of x, or quantile of x, okay, quantile of this function. So for example, we can derive this transformed uniform distribution. So we want to go from say 0 to 1 to a to b. So then f of y will be 1 over b minus a. So between a and b. So then we can use the same formula again here. Py dy becomes dy by b minus a, which is equal to dx, and then you integrate it to get from y equal to a plus b minus a x. Okay. Similarly, we can also go from uniform distribution. So here if x is, you generate x between 0 and 1, then transform x to y, and the y will be uniformly distributed between a and b. Now we do go from similarly go from uniform distribution to the exponential distribution. So suppose we want to have a PDF which is exponential of e to the minus y for all the y in numbers, and we are given a uniform distribution between 0 and 1. So we can apply the same principle here, and then we will get y of x as log of minus log of 1 of x. Now if x is distributed uniformly between 0 and 1, y will be distributed exponentially between 0 and infinity. Okay, so you can do this exercise as well. Okay, now similarly we can also generate Gaussian PDF. So, but in this case, analytically it is difficult to find the inverse, since the CDF is an error function, but you can do it numerically. Okay, so but there is another solution to do this analytically. So instead of generating one uniform distribution, you can generate two uniform distributions. One is P of phi, which is 1 between 0 to 2 pi, and another distribution, another exponential distribution, e to the minus t, where t is between 0 and minus infinity. Okay, I think e to the power t, t goes 0 to minus infinity, t to infinity. Then from this we will obtain two Gaussian distributions, gx and gy. Okay, so we can have product of two distributions. So we can write the product of two distributions here. It's equal to the product of two distributions, Gaussian distributions, and from there we will have this kind of equation. This side is exponential times uniform, and this side is product of two Gaussian. Now you can do a transformation of coordinates from rectangular to polar, okay, with 0 equal to square root of 2t, and and then you will get x is square root of 2t times cos phi, and y is square root of 2t.
There is, sir, excuse me, there is one correction. The error function of x equal to 2 by root pi.
Okay. So I then have to correct this.
Thanks.
Okay, thank you. Okay, so so if you do such transformation, you will end up with x and y both distributed with Gaussian PDF. So you generate one uniform, maybe you can generate two uniform, then convert one to exponential, and then you do this variable transformation with that, and you will end up with two Gaussian distributions, x and y, both are distributed according to Gaussian PDF. Okay, so this is very simple. I think you can skip it. Yeah, so here is another exercise. So I'm sure you have studied already this in maximum likelihood method. So I give you this exercise to do the maximum likelihood, just verify the maximum likelihood estimate. Okay, so consider an exponential PDF, which is typically the decay of an unstable particles, which is given by this PDF, where tau is the mean lifetime. Okay, and suppose we have data for n decays, and we want to estimate the value of tau. What is the value of tau with n decays? So we can use the maximum likelihood method, and we can maximize the log likelihood function with respect to tau to get the estimate for the to get its estimate, right? That is what you have studied in the maximum likelihood method. So here the log likelihood, the likelihood function for tau will be product of the probabilities, okay, for n data points. and then we can take the log of the likelihood, which becomes sum. So we always maximize log because log becomes from product to sum, and maximizing this becomes easier. Okay, and the maximum of log of likelihood is at the same point as the maximum of the likelihood. So from this you can say that this becomes sum of log of 1 over tau minus di by tau, and when you maximize this with respect to tau, then we get the estimate for the tau, okay, which is 1 over n, or the average of t of phi. So the average of t of phi is a good estimator, or for the as an unbiased estimator for the its lifetime tau, okay, for the for the parameter tau. So you can also show that. So you generate a large number of, say, random numbers, okay, from this PDF, and then you just, so you assume some tau values, say 1 or whatever, and then you generate large number of random numbers as like you are getting it from the data, okay, and then you take average of this, okay? And this should correspond to it should give your estimate value should be pretty close to the true value of tau, okay. So this exercise you can do, and as you increase n, you can try to do it for various n. So first small number of random numbers, then you increase this, and you see how the accuracy improves. As you increase n to very large value, it should become very close to the true value of tau, okay. Okay, so you can do this exercise as well, and you test your understanding of what you understood from the maximum likelihood. Okay, now let's see what are the difficulties in transformation method. So we said that we can transform one from uniform random numbers to a desired PDF, but there are some difficulties.
Excuse me, sir, in between. Sorry to disturb you.
Yes.
Uh, sir, is it possible for us to do any numerical question in between? The likewise you have done. You have told us about the transformation method. Will we do one question based on it, or one problem based on it, which is not specific to any subject, specifically like physics or mathematics? Any general question will be? Is it possible for us to do?
Yes, so I think I said many general things, like these are not any mathematics. Like I said, you can just test the central limit theorem, simply add large number of uniform random numbers and see the PDF of the average. This is nothing related to physics, just statistics, right? You are just taking the central limit theorem, you can do that. Even this one also you can do that. This is not okay. This is not Indian. Okay, it is related to physics. This you get this kind of distributions when nucleus decays, but you can even try to do this. It's just a simple PDF, and then you just generate it using PDF. So you just call exponential PDF. Okay.
Thank you, sir. Thank you.
Yeah. Okay. Thank you. So if you know Python, Python has all this. In Python, you have routines to call different PDFs. And you generate random numbers with different PDFs. So you can call just the function and then you calculate this. Okay.
Thank you, sir.
Okay. So now let's see what are the difficulties in the transformation method. Suppose we want to generate random numbers distributed according to some PDF. Say in this case, say P of y is a plus a times a 1 plus a y square. Y is distributed between -1 and 1. Okay. Then we can find a, which is a constant, and we can normalize P of y and to get what is the value of a. Okay, so that P of y should be normalized to 1 between -1 and 1. Now we want to we generate random numbers using uniform distribution, and we want to get this distribution P of y. So using the previous conservation of probabilities, we will end up with x equal to -1 to y a of f of y p of y dy. Okay, while x is distributed between 0 and 1. Now that gives x equal to this. So now you have to invert this function to get the value of y, right? And this is a third degree equation, so you cannot invert this analytically. So one must have to do numerical methods, must be using numerical methods to solve this equation to find y for each given value of x, right? Okay, so this is one difficulty. So one have to do many times. You have to do numerical. You have to resort to numerical methods to invert this function. So the steps normally are the following. Okay, and these are the kind of things that are implemented also, in the programming languages. So what they do is that you decide on which range you want to generate y. Okay, if the range is infinity, you have to choose some reasonable finite limits, very large number basically. Then normalize the probability density and adjust it so that you renormalize it so that the total probability becomes 1 between your range. And then you generate a uniform random number variable x. Then you integrate the normalized probability function p of y from lower limit to the value. So you end up with x equal to y lower to y p of y dy. Now you have to invert this function. So this inversion, as I said previously, in this case you have to do numerically, right? So one trick is that before you do this, you can have a root, you can have a table like for each x, for each x you can generate y, and you keep this number for a large number of points, kind of a table. Okay, and then for every time you generate an x, you can find the corresponding y values. Otherwise, every time if you want to do this computation, it is computing intensive. And if you have to find some numbers in between the two numbers you have stored in your table, one possible way is to do the interpolation method, okay, instead of doing this computation. Okay, that was about generating random numbers with different PDFs. Now let's come back to again the sampling method. So we had discussed earlier the food integration method or brute force integration method. Now suppose we want to perform again this integration of f of y dy between a and b. Okay. Now in this case, now let's assume that p of y is a PDF whose behavior is very similar to f of y, the function you want to integrate. Okay, in this interval a and b. Now the normalization of the condition of the PDF gives you that the integration over p of y dy is 1. Now we can rewrite this integral, the above integral, this one, as integration of this as we can multiply p of y and divide p of y here. Okay. Now if we generate a random number uniformly with a uniform PDF distribution p of x, now by performing this change of variables that we discussed earlier, we go to a p of y this PDF. Okay. Okay. Now we can write like this. So p of y dy can be written as px dx. Okay, from our earlier conservation of probabilities, and so then this integration will become instead of y we will be doing integration over x, while y depends on x. So we can get for each x, we can get the value of y, right? And the integration range changes because now this integration range becomes for the x, not for the y. Okay, for the corresponding integration limits for the y, we'll find what is the integration limits for the x. Then this MC integration will become average the way we did earlier. So now we can treat this f of y over p of y as a single function, some f tilde, and that we can write like earlier we did. This becomes an average. So this is average of I equal to 1 to n, this function, whole function here. So the advantage of this is that this is called input and sampling method. The advantage of this is that,
sorry to interrupt, sir, but in the first equation, the py, where it is absorbed?
this one, so py dy is px dx, right? If we do variable transformation, so x is our x, if we are generating a uniform random number with a random number with uniform distribution. So x is a uniformly distributed random number. So px is 1. So we can write py dy as px dx, while y depends on x. And then px is 1. So here what we replaced is that we replaced pi dy by px dx, and px is 1. You remember the previously we did this, the same thing here, right? So here px is 1. So this is a conservation of probability. So we go from one variable to another variable. So one is distributed from uniform distribution, another is distributed with your desired PTM. So we are transforming one variable to another variable. In this way, we can write f of p of y dy as dx, because px is 1. Is it clear?
Yes, sir.
Okay. So, okay, now we get this average. Now this average is not only on f, but on f over p for y, okay, while y depends on x. So what you do, you generate xi's uniformly, transform the xi's to y, okay, using variable transformation, and then calculate f over p, and then take the average. Okay. So the advantage is that if py follows very closely to f, okay, then this ratio becomes more or less flat, right? Because p is pretty close to f, the distribution, then this ratio will become more or less flat, okay. So our sampling becomes better, okay. Otherwise, if suppose f was varying very differently than uniform distribution, and we are generating numbers using uniform distribution, then we are not sampling it properly, okay, for this function. Now this way we are sampling this in a better way, and that's why the accuracy improves, okay. So one can also calculate the variance using this method. Okay, now I give you another exercise, so you can try this. Suppose we apply this method of impedance sampling to compute an integral e to the x dx. That integral value you know, right? What is the value of e to the x dx? Now, instead of we want to do this using Monte Carlo simulation, so you can use a PDF p of x is 2 by 3 times 1 plus x, and generate random numbers using this probability distribution between 0 and 1. And using these random numbers, evaluate the integral using the method that I discussed, the impedance sampling, and also check the accuracy of this with respect to brute force method. Okay. So here, if you transform from uniform distribution to this distribution px, then you have to do this following transformation. Okay, so you generate y as uniformly distribution, then from this to go to x, which will be distributed according to this distribution by transforming this way. So y is generated here as uniform, and then you do this transformation, the x will be generated with this distribution, and then you use f of x by p of x and calculate the mean for the n number of points. Okay, and then see what is the value of this integral, and you can compare this to your exact calculation. So I give small simple exercises so that you can cross check the numerical calculation with the analytical calculations. Okay, so another method is the acceptance rejection method. So this is the one in mostly used. In many cases it is used. It is very simple. So suppose you want to generate a PDF which is distributed like this, okay, according to this function. Okay. Now, what you can do is you can enclose a box around this, okay, corresponding to the maximum height of this function f max. Now you generate a random number between 0, a random number x between 0, this x min to x max here, and simultaneously you generate another random number y between 0 and f max in this region. Okay. Now you compare for each x, compare the value of y to f. Okay. So for each x, you generate y. If y is less than f of x, y falls inside this, then you keep the x, otherwise you throw the x. So this is called acceptance rejection. So you basically generating a 2D random numbers, okay, filling this box and keeping only x when y falls inside below this curve. Okay. So that is called acceptance rejection method. So it's the simplest way, and you will always get the your desired PDF. Okay. So here you can see, for example. So here, for example, you want to generate a PDF, a function, a PDF which is given by this function, distributed between -1 and 1, and so you generated all these points, and then you only keep x when this one, the y value falls below this curve, and then you take the distribution, look at the distribution of x in one dimensional, then you can see that they are distributed according to this. So this is your PDF. If you do it for large number of points, these fluctuations will go away. It will become more and more smooth, and you will get this PDF, which is distributed according to this PDF. If you have less number of points, you will have more fluctuations. If you have large number of points, you will have less fluctuations. Okay. Now I give another exercise or example. You can do this as well. Compute the value of pi. So you know that the value of pi you can compute if you take this square and then take the area defined by this circle, 1/4 of that circle, okay, with the same radius as the size of the square. Okay. So then the ratio of the area of, so area of the square is 1 if I take the side is 1, and the ratio of the area of this curve, under this curve, to the total area of this square will give you the pi by 4, right? Because the total area is pi r square, so you take pi r square by r square gives pi r square. Here is pi by 4 r square because we are taking 1/4 of this area, or 1/4 of the circle. So pi by 4 r square divided by r square, so gives you pi by 4. So you generate two random numbers x and y between 0 and 1, and you only number which is when this condition is satisfied, x square plus y square is less than 1, and then count the number of total numbers that satisfies this condition divided by the total number of numbers you generated. Okay, so that ratio will give you 5/4. As you go to very large number of points, you will see that you are getting pretty close results. Okay, now I think I discussed the methods for generating random numbers and how to use them and do some simulations using this, and also I gave you some example from the statistics like using it for doing maximum likelihood fit. I just have 2-3 slides to explain you what is Markov chains. So typically, actually in many cases, you may have heard Markov chain Monte Carlo. Okay, so Markov chains are used to generate Monte Carlo, used to do the Monte Carlo simulation. So generate random numbers which can be used for Monte Carlo simulation. Okay, so what are Markov chains? So Markov chains are, it's a stochastic process where given the present state, the past and the future states are independent. So the future and the next one depends only on the present, doesn't depend on the past. Okay, such chains are called Markov chains. So consider a sequence of random variables, for example xt, t equal to 0 to 1. So xt may have a finite or countably infinite number of possible values, which we call the states. So the state space is containing all such values of xt. Suppose the probability for state I at a time t to change to a state j at time t plus 1 is Pij, with index Tij defines the time. Okay. Now this sequence will be called a Markov chain if the probability of finding xt plus 1, that means the next state becoming a state j given all the previous states, okay, is equal to the probability of getting the next state given only the present state. That means it doesn't depend on all of its history. Okay, it doesn't depend on the previous ones. It depends only on the present one. Such sequence are called Markov chains. So from the previous relation, we can say that the probabilistic properties of the chain are completely determined by two things: the initial distribution x0 and the transition probability Pij for a transition from state I to state j. Okay, and if the transition probabilities do not depend on the time, that means they are homogeneous, independent of time, then they are called normally homogeneous Markov chains. So, as I said, the Markov chain is governed by a transition probability matrix. Okay, so assuming n states, all integer valued, the transition probability will be basically a n cross n matrix with elements Pij, which gives you transition probability going from ith state to jth state, and these probabilities have the probability a value between 0 and 1 as any other probabilities, and sum of all this probability becomes 1. Okay. One example of Markov chain is a random walk. You may have heard it. Okay. So consider a random walker in one dimension. This is just one dimension. Okay. The probability for moving left or right on the line from its current position is governed by a probability function f, and xn represents its current position. Okay. So giving a current position, it has a probability to go to left or go to the right, which is given by some function. Suppose we start with a position x0, okay, and then the positions at a given time or given step n can be written like this. So xn, we can write xn equal to xn plus omega n. Okay. So omega n is some independent random variable, so it's some probability function f of x. Now we can write again xn plus 1 will be xn minus 1 will be xn minus 2 plus omega n minus 1, and so on, so on. So at the end we'll get this sum of all these numbers. So starting from 0 we'll end up with xn with sum of these numbers. So xn's, all these xn's will be a Markov chain. So the position at a given instant n will be described by the probability. It will be described probabilistically by this distribution of sum of omega n's. Okay. Now you can consider what are the probabilities. Suppose our probability for going right is p, probability for going left is q. So you are at a position, the random walker is at a position. He has a probability to go to right as p, probability going to left as q, and probability being remain at the same point without taking any step, maybe r. Okay. So then the sum of this probability will be 1, and then you can define the transition probabilities for going to left and right. So px going from xn to xn plus 1 will be p if xn plus 1 is xn plus 1 is xn plus 1 going right, or if it is xn minus 1, that means going left, or if it remains at the same point. So these are the probabilities. Depending on, so for each step you can only say that what is the probability going to the left or right or remain at this point. So it will depend only on that state. It will not depend on any other previous state, whether where it started from. Okay. So I actually skipped many things about the Markov chains. So there are some theorems and there are some properties that Markov chain has to satisfy to be used in the Monte Carlo simulations. So those properties, if the chain satisfies such properties, if you generate the Markov chain for a long enough time, you can get a stationary distribution. And if you choose that stationary distribution to be your desired PDF, okay, then you will get your PDF starting from some arbitrary points. If you generate large number of points, you will generate your desired PDF. Okay. So one of the algorithms which generates or are used to generate the Markov chain is called this Metropolis Hastings algorithm. So suppose f of x is your target distribution. So you want to generate f of x, maybe Gaussian or maybe exponential or something. Okay. Now you can start with some initial value x0, arbitrary initial value x0, drawn from some random distribution, some starting distribution g. This can be flat uniform distribution, it can be Gaussian, or it can be other distribution, any uniform distribution, any other tracking distribution, which f of x0 is greater than 0. Okay. So given x0, the algorithm then produces a sequence of random numbers, variables, following this step. So you sample a candidate from the proportional distribution. So G is called the proportional distribution. So you start giving some G x0, you start with a seed. Okay. Now you generate a next number from this proportional distribution. So you know the proportional distribution. Say like I take uniform distribution as my proportional distribution. Now I generate the next number. Now you have a algorithm to go to the next depending on whether it satisfies some conditions. Now you compute this Metropolis Hastings ratio R, which is defined like this. Given xt, you go to x star. Okay. If it should be xt plus 1 star. If x, if you define this ratio as f of xt plus 1 by f of xt times g of xt given xt plus 1 by g of xt plus 1 given xt. Okay. Now you will see that this ratio will be always defined, since the proportional distribution for xt plus 1 can only occur if f of xt is greater than 0. Okay. And also this is greater than 0. Now you can sample the values xt plus 1 according to the following probabilities. So you keep xt plus 1, okay, with a probability alpha, which is given as a minimum of r and 1. So that means if r is greater than 1, you take probability 1, or if r is less than 1, you keep them with this much probability. Otherwise, you just retain the previous number. Do not, that means reject the next number, and you keep the same number, and then again draw a next number to compute the r. Okay, so you keep repeating this procedure. Okay, so this is, I made a flow chart for this algorithm. So what you do is the following. So you choose an initial state, for example some position xi. You suggest a move x star using your proposal distribution G, for example uniform. Compute R values. Now you generate simultaneously a uniform random number small r, which is distributed between 0 and 1. So this is to satisfy this criteria. Okay, this criteria here, to keep with a given probability. Now if r is greater than or equal to r, okay, you reject, sorry, if r is greater than or equal to r, you keep this xt, okay, you keep the next the number that you generated xi plus xt plus 1, and if it is not, then you reject this number, you keep the same number xi, and you go back to the generating a next move. Okay, and when, if it is next, you collect this sample and then reassign xi plus 1, and you go back, start again from xi plus 1 and go to xi plus 2, and so on. So that is the algorithm. And so here you can see an example taken from this book, a sampling from two-dimensional Gaussian distribution using this metropolis algorithm, in which case the proposal distribution is an isotropic Gaussian. Okay. So you start with an isotropic Gaussian. So here you want to generate a two-dimensional Gaussian, which one sigma contour is given by this black line. Okay, so you want to populate this distribution, and then you start with some arbitrary point. Use a proportional distribution which is an isotropic Gaussian with a standard deviation 0.2, and then you move. Okay, as it moves, as you can see, the points which are accepted are given by this green line, and the points when it moves out of, you can see many times whenever it moves out of these lines, theirs are rejected. So the red ones are the ones where the proposal is rejected, and the green ones are the ones where the proposal is accepted. So you can see that the acceptance is more which inside this 1 sigma contour, while rejection is more outside the 1 sigma contour, but you will have some acceptance also outside. So you can see that in this case a total of 150 candidate samples are generated, and from which 43 candidates are rejected. Okay, so this is an example. So in fact I wrote a small program also, where I can start from say uniform distribution and uniform proportional distribution, and then I end up with, if I want to have a desired PDF like say x square distribution or Gaussian distribution, I can get a desired PDF from that using this MH algorithm, Metropolis hashing algorithm. Okay, so I think I didn't discuss this topic is also very large, so you need to there are a lot of things. I just gave you very briefly what is called the Markov chain Monte Carlo and Metropolis algorithm. So if you need more information, I think you can either study it or you can have some separate lecture on that. Okay, so these are the references in case you want to go into more details into Monte Carlo simulation. Yeah, that brings to my end. Thank you. So if you have questions, I'll be happy.
Excuse me, sir.
Thank you, Arun sir, for such an informative talk. Now I request the audience to ask question one by one.
Excuse me, sir.
Yes.
Yes.
Sir, in the Monte Carlo method, we have told that when we are taking the integration of a function in a given range a to b, then it will approximate to an average. But sir, integration is mostly taking the area under a curve. How is it approximate to an average of that function?
Yeah, so what you are doing by averaging is basically you are doing calculating this area under this curve by this method. So you populate large number of points, okay?
Okay, sir.
Under this curve, for this curve, right? You are
Yes,
populating large number of points for this curve, and then you are taking this average. So yeah,
sir,
when I said this one, so here what you are doing is you are generating large number of points for these functions, and then you are taking the average of for those points.
so
As
sir,
you can
first
see,
we are calculating the integration, then we are averaging the function.
we are not calculating the integrations. So you can see that I mean the integration is equivalent to this average as we said here, not here. So
Okay, sir.
so we computed here the integration, right? So you can see that this integration is kind of an average, isn't it?
Yes, sir.
Using the numerical method. So when we take this midpoint method, so we are
Okay, sir.
averaging it for all these grid points, right?
Okay, okay, sir.
So in this case, we are basically doing the same.
Okay, okay. Okay, thank you, sir.
Yes, is there anyone else who wants to ask anything? Sir, may I ask a question?
Yes, sure.
Sir, actually, I was wondering how a computer generates a random number. Like physically, we can generate random number by throwing a dart. We were discussing an example in which we were calculating the value of pi. That can be calculated by throwing a darts on that square.
Yeah,
But
that
how
is what
does
you are
a
doing, right?
computer generate?
Throwing the
How is a
you are throwing
computer
the dart.
generating? But computer
Exactly,
cannot throw the darts.
you are throwing the dart here. So throwing the dart means you are basically getting one point at a time, right?
Yes,
So you are taking the square, then you are throwing the dart. Throwing the dart means you are arbitrarily getting one point inside this region, right? That is what you are doing. So the random number generator generates one point every time you generate one point within this curve. So you are generating x between 0 and 1 and y between 0 and 1. So every time you get one point inside this area randomly, right? Just like equivalent to throwing dart, isn't it?
Sir, the question precisely was how can a computer throw a dart? How can it think of some random number?
No, it doesn't think. You give the algorithm to do this. Computer doesn't think. So we
But if
discussed
algorithm
right?
is given, then it is no more random.
Yes, so that's what it is called pseudo-random number generators. It satisfies randomness up to very large number. Okay? So this, as I discussed this algorithm, So if you generate this, random number starting from a seed, then you just draw these random numbers. Just see if there is any sequential behavior, or you just get a flat distribution. So the task I gave you here is to generate. You just write a few line of code, 2 lines. Okay. U xi plus 1 equal to xi plus b mod c. Okay. And you have give this value, and then you just fill a histogram with xi values. Okay. And when you fill this histogram, then you will see that you are basically getting a uniform distribution. So that means you are randomly generating. You do not have a pattern, right? And if you do the same thing simultaneously for two numbers distributed between 0 and 1, you can fill a 2D distribution, right? And you can see that for a 2D distribution, you will see you are filling the whole area uniformly. If it was not random, then you would not fill them uniformly. You will see patches, correlations between them, right? So
Thank you so much,
if they
sir.
are random, then you will see they are uniformly distributed within your area. So you can do this exercise with this algorithm. So that is the thing. So this has some sequential behavior, but the sequence is very large if you take a large number for C. So the repetition is very small. That's why you can treat them as random number. That's why they are called pseudo random number, not truly random. But they behave almost like a random number.
Okay,
But
sir.
every time
Thank
you
you.
start with the
Thank you so
same
much.
seed, you will get same sequence of events, same sequence of numbers. So if you want to get a new sequence, you should start with a new seed.
Mm-hmm. Okay.
Sir. Hello, sir.
Yes.
Sir,
I want to
can
ask
you
that
suggest?
distribution. How can we
Uh,
generate random number, sir? Multivariate, normal. By using this method.
Yeah, so you can have multivariate random numbers as well. So multivariate means what? You have for each variable, okay, so you have for each variable you have one random number, and you generate them simultaneously. Suppose, as I said, it's a two-dimensional Gaussian here in this case, right? In some case I said two-dimensional Gaussian. Here, for example, I discussed how to generate two-dimensional Gaussian. So if you do this method, you will get both x and y Gaussian simultaneously. So this is a 2D Gaussian, for example.
Hello, sir.
Yes, sir.
Yes.
Sir, can you suggest us some related literatures to how we use the Monte Carlo method in case of transit curve fitting of exoplanets? So, is there any related literatures that we can follow for particular this kind of purpose?
What was the problem? Sorry, I
Uh,
didn't get.
Sir, we use the Markov chain Monte Carlo methods to fit the transit curves of the exoplanets. Sir, is there any related literatures that you can suggest us to study?
Sorry, I am not an expert in those fields. I think you have to look at the papers in that field. I just told you how to generate Markov chain and how to use it. Then the problems you have to define and how you use it there for simulating this.
Okay, sir. Thank you, sir.
I'm not really expert in that field to suggest some literature. Yeah, please look at some papers and then you can try to use them. So idea is that you have some theory and you want to do some modeling using the Markov chain, and you generate Markov chain and you model your distributions given by your theory using the Markov chain uh, distributions, right?
Yes, sir. Sir, actually, I want to read about it, so that I asked you.
Okay.
I will look it for. Sir.
Yeah.
Thank you.
Okay.
Thank you, sir.
Um, so, is there anyone else with some question?
Sir,
It's very fine. Someone is asking something.
Yes, please go on. Ask your question.
sir, Markov chain and Monte Carlo techniques two are different from simulation. Two techniques are one technique is simulation, means Monte Carlo. Markov chain is also simulation process.
Uh, Arun sir, kindly unmute yourself. Actually, by mistake, you were. Uh,
Okay. So can you hear me?
uh,
Yeah. So
Yes, sir.
Bayesian is a technique to do Monte Carlo simulation. Okay. So Markov chain is basically a technique to generate random numbers, and it has a high speed and more randomness with a very high, periodicity and so on. Uh, so this is basically helpful for doing the Monte Carlo simulation.
Okay, okay, okay. Thank you, sir.
okay, so now I take the honor to thank Professor Arun Nayak for such an informative and such a basic talk on Monte Carlo methods. So we are indebted to you for your valuable time. Thank you so much for
Yeah,
joining and
thank you.
sparing your time.
It was a pleasure to give this talk, and I think there are large number of audiences. I hope you got some insight into these topics. So if you need any help, you can contact me in future.
Yeah, thank you,
Thank you,
Professor,
sir.
for joining us.
Thank you for inviting me in first place in giving these lectures.
So
It was,
Thank you,
helpful
Arun.
to
Thanks.
gain some
Thank
knowledge.
you, Arun, for giving more insight. Thanks.
Thank you. Okay,
thank you.
bye.
Bye, guys.
Thank you, sir. Thank you so much for taking out time. Yeah, thank you.
All the
Okay,
participants are requested.
yes, Ankush, go ahead.
Okay, so all the participants are requested to kindly fill the feedback form. The link has been shared in the chat box.
Okay, and so today there is no another talk, and the last talk of this workshop that will be tomorrow morning at 11 a.m. Okay, so
Okay.
we will.
What about feedback links?
Feedback link we will share on the that is already shared on the WhatsApp group.
Okay. Thank you.
Yeah. Thank you very much.
Hello. So there will be no lecture in the evening today?
Yes. For today, there is no lecture in evening. Next lecture is scheduled to happen tomorrow.
Tomorrow, 11 o'clock. So following this, there will be no lecture like today. After Mr. After this lecture, there won't be any other lectures, right?